I've got another circuit for you today. It's another sawtooth oscillator. This one's a little bit simpler than last time, and it uses a MOSFET. Okay, so let's dive into this circuit diagram. Just like before, we have this voltage-controlled current source. Right now, we're going to split somewhere between ground and 12 volts, and we're just going to kind of copy that onto this point here, right, which forces some fixed amount of current through this resistor here, which we can choose, and that pulls the current down here. But of course, this will only pull it down as far as ground, right? And we want that capacitor to go down below ground, so we have this mirror. So we're going to be able to pull it all the way down to minus 12 and all the way up to plus 12. Okay, so the current's coming through here, and basically we're always charging this capacitor. This current is always flowing through here, charging this capacitor here. So that'll give us that linear ramp. What are these things doing here? Well, when this MOSFET closes, when it lets current through to suddenly drain that capacitor, it's a big spike in voltage. And so we put this resistor here to slow it down a little bit, because that capacitor can source a huge amount of current when the voltage changes. And so we slow it down a little bit with this resistor, and then these diodes here, you'll notice they kind of almost look like they're backwards, right? It's preventing current from coming from plus 12 to minus 12. What happens is if this goes above 12 volts, it'll shunt that current out there, right? And it'll help protect some of the other parts of the circuit. Okay, so we're charging this thing constantly until this gets triggered. And this is triggered whenever this gate, which is coming from over there. And I set up this constant voltage just sitting here at minus 6 volts. And so this capacitor will charge up and up and up until it reaches some threshold. This gate will close, and whoop, it'll pull it down to minus 6 volts, whatever's here. Okay, so that threshold is very simple. It's just a Schmidt trigger. We just have equal resistors here. So that means that the thresholds are minus 6 and plus 6. Now, when this capacitor is high, it hits the high threshold, right? It's going to cross over the plus 6, which is going to make this thing go down to minus 6. Now, to turn this guy on, we need a positive voltage, not a negative one. So we have this silly little inverter sitting here. And now, we see these 3 resistors here. It almost looks like a voltage divider, right? Now, if these were significantly, or if these were about the same size, the 10K, 10K, 100K, if this R5, if it were small like this, then we would have almost a voltage divider. The way I've set it up here, with this being 10 times as large, basically this acts as it did before, with a minus 6 plus 6 threshold. And then this here, this is an inverting amplifier. I've used larger resistors here so that these ones don't impact the circuit here. It's almost like, from this guy's perspective, this whole part of the circuit is removed. And this side of the circuit is just going to amplify whatever's over there, and it's an inverting amplifier, so it'll flip it around. We have this 5.6K resistor here, which just to kind of slow the discharge down a little bit, so that when we do close this here and allow that current to drain out of the capacitor down to minus 6 volts, it's not happening too fast. And so that gives us a nice adjustable ramp rate and a very quick fall. And I'll show you it here on the PC. I mean breadboard, of course. So let's power this up. We're draining 30 milliamps until those capacitors charge. I have some really large capacitors over here that I use to remove any ripple from my power supply. And let's go for broke and just probe this capacitor here. Oh, there, do you see it on the scope there? There we have, it's reading, what, 284 hertz. And if we turn this pot down, we get still 284 hertz. What's going on? Let's turn it up. I just don't have enough hands to hold everything. I've turned that pot down, and now we're down to 138 hertz. I guess we can turn it down further. Yeah, my scope doesn't want to measure things less than this, but we're down to 83 hertz here. So we probably need to get some more current going through there, get some frequencies that are higher than the 200s. This is kind of like a middle C around there. But just a smaller resistor, and we should be able to go up to all of the musical notes. Down, 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 down. Oh, it's going crazy. Can we do this? Yeah, it's slow. Okay. Yeah, it says that down here at the bottom, down to a few hertz. Yeah, my meter, my scope here isn't really too happy at these lower frequencies. But there we're down to 43. It says 25 hertz now, 23. Yeah. Yeah, that's definitely kind of near the bottom. 19 hertz. Cool. So why did I use a MOSFET in that circuit? Well, honestly, just because I couldn't get a transistor to work in real life. The transistor was working fine in simulation, but in real life, the MOSFET was doing the job. There must be something wrong with the biases or something like that. Something I need to learn about. But anyway, I think it's pretty cool that we have a simpler sawtooth wave there. And I'm looking forward to doing more with this. Right, so thanks for watching. As always, let's do this together, and I'll see you next time.